66 million years ago, Earth was not empty. It was alive with dinosaurs that had dominated land ecosystems for more than 160 million years. They were not movie monsters. They were animals. Plant eaters, predators, nest builders, migrators, parents, and survivors of an ancient world. Then, in a short geological moment, the non-avian dinosaurs disappeared from the fossil record during the Cretaceous-Paleogene extinction event. This extinction wiped out about 3/4 of Earth's species. But the real question is not only what killed the dinosaurs, it is what happened to Earth after they were gone. Before the extinction, dinosaurs filled many of the major land animal roles. They browsed, hunted, scavenged, defended territory, and raised young in complex ecosystems. Mammals already existed, but most were small. Many lived in ecological shadows, while dinosaurs dominated large land animal niches. For decades, the extinction was a mystery. Then scientists studied a thin global clay layer at the boundary between Cretaceous and Paleogene rocks. That layer contained unusually high levels of iridium, an element rare in Earth's crust, but more common in asteroids and meteorites. Scientists also found shocked quartz, glassy impact particles called tektites, and other signs of an extreme collision. These clues pointed to an impact, not ordinary climate change alone. The impact site is Chicxulub, near today's Yucatan Peninsula in Mexico. The buried crater is about 180 kilometers wide. The asteroid was probably around 10 kilometers wide. That sounds small compared to Earth, but at cosmic speed it released energy on a planetary scale. When it struck, rock was vaporized, molten debris was launched upward, earthquakes shook the crust, and tsunamis moved across ancient coastlines. Near the impact zone, many organisms would have died quickly from heat, blast effects, earthquakes, falling debris, and massive waves. But the extinction was global because the impact changed the atmosphere. Dust, soot, and sulfur-rich aerosols rose into the sky. Chicxulub struck rocks that included sulfur-bearing minerals. When vaporized, sulfur aerosols could reflect sunlight back into space. The result was an impact winter, a period of reduced sunlight, cooling, and environmental stress across the planet. The most dangerous effect was not that every dinosaur was hit directly. It was that sunlight fell, photosynthesis weakened, and food chains began to break. Large plant-eating dinosaurs needed vegetation. When plants suffered, herbivores suffered. When herbivores declined, predators lost their food. This was not only a dinosaur extinction. Ammonites vanished, many marine reptiles disappeared, many plankton groups were damaged, and flying reptiles died out. In the oceans, photosynthetic plankton sat at the base of many food chains. When sunlight dropped, marine ecosystems were hit from the bottom upward. Impact gases may also have contributed to acid rain and ocean chemical stress, especially for organisms that depended on carbonate shells. At the same time, enormous volcanic eruptions were happening in India, forming the Deccan Traps and releasing climate-changing gases. Some scientists think volcanism may have stressed ecosystems before or after the impact. But the strongest evidence still points to Chicxulub as the sudden main trigger. A simple way to say it is this: volcanoes may have stressed the world, but the asteroid delivered the sudden global shock recorded at the KPG boundary. Survival depended less on strength and more on lifestyle. Small animals could hide, burrow, scavenge, eat seeds, or survive on less food. Crocodilian relatives, turtles, frogs, insects, fish, small mammals, and some birds survived because their lifestyles gave them options in a damaged world. Many non-avian dinosaurs were large and needed stable food supplies. In a collapsing ecosystem, size could become a weakness. But dinosaurs did not completely disappear. Birds are living dinosaurs, descended from theropod dinosaurs. The surviving dinosaur lineage had feathers. So the accurate statement is this: non-avian dinosaurs went extinct, but avian dinosaurs survived and later diversified into modern birds. After the extinction, many landscapes were disturbed. In some fossil records, fern spores become very common, a pattern often called the fern spike. Recovery happened in stages. First, life survived. Then disturbed ground was recolonized. Later, forests and food webs rebuilt. Then new species diversified. With many dinosaur niches empty, mammals had new opportunities. Over millions of years, they evolved into larger herbivores, predators, climbers, swimmers, and eventually primates. This does not mean humans were destined to appear. Evolution has no script, but the extinction helped open the road mammals would later travel. Dinosaurs were not failures. They dominated land ecosystems for over 160 million years. Modern humans have existed for only a tiny fraction of that time. The lesson is vulnerability. Even dominant life forms can disappear when climate, sunlight, oceans, plants, and food webs change too quickly. Today, Earth is changing again. Not because of an asteroid, but because of human activity, habitat destruction, pollution, climate change, and species loss. The dinosaurs could not see their disaster coming. We can see ours. We can measure warming, count species loss, and watch habitats disappear. Protecting Earth is not only about saving animals. It is about saving the systems that allow life to continue. Forests, oceans, wetlands, soil, insects, and climate balance. Extinction is not just the death of a species, it is the end of a story that took millions of years to write. Earth can recover, but it does not rewind. The asteroid ended the world of the non-avian dinosaurs, but it also reminds us that no species owns Earth forever, not even the giants. And if we are wise enough to understand the past, maybe we can be brave enough to protect the future.